Okay, welcome to the lectures of Power System Dynamics and Control course. So, last lecture we discussed the turbine and governor system modeling. So, in that we have discussed the modeling of hydro turbine and steam turbine in detail, and also we discussed the governor system modeling. Okay. So today we'll see the modeling of the load, how the load we can model. Actually, if we'll see in the power system, when we consider a large power system, large network, each bus in fact will represent the distribution substation, or you can say from where the distribution system is connected. And therefore, in each bus, whatever load is representing in each of the bus, like for the high voltage power system we are talking about. So in each bus, the load representing the say the combined load of that distribution point from where it is being distributed to the consumers. Actually, individual load modeling is very difficult in large scale power system. When we are analyzing a large power system, it is difficult to consider the individual load models. So therefore, in segregate, we can say in a combined mode, we cannot segregate. In a combined representation, we can model the load. So we'll see how we can do this. Okay, so before that, we have seen in the last class this turbine governor modeling already. It is discussed very elaborately. I discussed around 30 minutes very elaborately. And finally, we found this equation as the model for the mathematical model for the governor system. So finally, we got the equations for the synchronous machine along with the turbine system, along with the governor. These are the equations. So this is the starter voltage equation, the differential equation, and these are the rotor differential equations. And this is the swing equation, which shows the electromechanical load, electromechanical modeling of the rotor dynamics. And then this is your algebraic equation related to the Fox linkage. Okay. Apart from these equations, we have exciter equation. These are the exciter equations, right? This is the volt. This represents the voltage regulator. This represents the rate feedback, and this represents the saturation effect and the field. And next we have seen the representation of load, and if we are considering a steam-based synchronous generator, then obviously this is the turbine reheater model, right? Then the steam chest, including high voltage turbine, and this is your governor model, right? So this is the whole, this three equation for exciter, and these three equations are for turbine and governor system, right? So therefore, we have finally achieved the model of generator. And now the question is how to model the loads. These are the various components we are modeling. Because generator and load, they are playing very important role in the power system. Then, of course, transmission line and representation of transmission line, of course, it will be taught you in the future classes. So now we can see the load representation. So The loads can be represented as either static or dynamic loads. Generally, lighting and heating loads can be represented by static models and which take care of everything. Whereas to represent the motor loads like synchronous motors and induction motors, the motor dynamics have to be taken into consideration. Then we'll see the static load representation. So the static load representation, if we'll see, static load representation is a simple way of representing the effect of load on the system stability. Okay, so then how it takes into account the system stability, we'll see. The effect of change in the voltage and system frequency can be incorporated in the static load model. This can be incorporated very easily. Therefore, it has effect. We can represent the effect of load on the system stability. So usually instead of representing each static load separately, an aggregate load is represented like all loads at particular distribution station can be clubbed together and represented as a single load, as I mentioned earlier. The typical way of representing static loads is either as a constant impedance load or constant current load or constant power load. Okay. So what is then constant impedance load, constant current load, and constant power load? Let us see. So if let us say PO, QO, and VO are the initial real power, reactive power, and voltage, these are base values we can say, then the effect of change in the voltage and the static load can be represented as this. So I can write the active power as a function of voltage like P naught. P naught is your base power into V upon V naught. V naught is the also base voltage to the power NP. NP is your exponential. And here reactive power also can be represented as the base reactive power Q naught, then V by V naught to the power NQ. NQ is also exponential. And where PQ are the real and reactive powers at changed voltage. So these are the changed voltages. So therefore, the power and the real and reactive power, they both are actually taken into account. They're taking into account the voltage effect, right? So in case the above equations are representing single loads, then NP and NQ, when taken as 0, represents constant power load, okay? And when it is taken as 1, it represents constant current load, and when it is taken as 2, it represents constant impedance load. So how it is? Like we can see here that P equal to P naught, V by V naught. If your NP and NQ they are taken as 0, then to the power 0 will be equal to P naught. So this represents a constant power load, right? Now if I'll take P equal to P naught, V by VO to the power 1, so here it will be PO, V by VO, right? Now, if I can see that this PO and VO they are constant, so therefore I can write P by V equal to PO by VO, right? So PO VO is constant, so therefore this represents a current term, right? P by V. So therefore, this kind of load, when the exponential is 1, it is known as constant current load. Similarly, if I represent P equal to PO, V by VO square, similarly I can write this as PO by VO square equal to P by V square. Okay. So of course, this represents an admittance, just taking the reverse, V squared by P equal to VO squared PO. So this is a constant term, right? And this represents an admittance, impedance, right? So therefore, I can say this load, when I take the exponential as 2, this will represent the constant impedance load, right? So I hope everybody understood. Now we'll go ahead. So for aggregate loads, NP, NQ may be chosen to approximate the actual behavior of the load and may be in the range of 0.5 to 1.8 for NP and in the range of 1.5 to 6 for NQ. Okay, for aggregate load. So a polynomial mode of load representation can also be used, which includes all types of like constant impedance, constant current, and constant power load, and we call it ZIP load. ZIP, constant impedance, constant current, constant power load. And it is shown as here, like P equal to P naught into PZ V by VO square plus PI V by VO plus PP. Okay, so this is combination of all kinds of load. This part represents your constant impedance load. This part represents your constant current load. This part represents your constant power load. Similarly for reactive power also, this is constant power, constant current, constant impedance, constant current, constant power, right? Now, where the PZ, PI, PP and QZ, QIP, QP are constants representing the approximated fraction of the aggregated load taken as constant impedance, constant current, and constant power loads. Though constant impedance are practical loads like lighting and heating, constant current and power loads are not real loads. Okay, they're actually certainly they're not representing any real loads. Like constant power loads, the constant impedance loads are practical loads. They're like lighting, heating, right? But it can be used to represent dynamic loads like motors, like this constant current and constant power loads. They can be used generally. Sometimes we use constant power load in load flow analysis, right? So they represent generally the dynamic loads like motors as static loads, and assuming that after disturbance the motor loads will reach their steady state rapidly. So this is the assumption, right? After the disturbance, the motor loads will reach their steady state very rapidly. But it doesn't happen when the motor load is very large. Like if we'll see a large motor is installed, it doesn't happen so easily when some disturbance takes place. But for small motors, it may happen. Therefore, to represent the aggregated small motor load, motoring loads, industrial motor loads, we can represent constant current and constant power loads. But for large motors, it is not possible. Hence, it is necessary to take the effect of frequency variation also on the loads to improve the accuracy and can be represented as this. Because the frequency effect is not considered, because frequency also affects the large motoring loads, right? So therefore, it is very essential to take the frequency effect. So therefore, along with the ZIP model, the frequency effect is added. It is multiplied one term, 1 plus kpf delta f. So one ZIP model will be remained and another term will be multiplied with kpf delta f, right? Similarly for reactive power also, this represents the ZIP model into 1 and again the ZIP model is multiplied with kqf delta f. So in above equations, the effect of change in the burst frequency from the steady state frequency delta f equal to f minus f naught is included in the static load model with constants kpf taking a value between 0 to 3 and kqf taking a value between -2 to 0. If the burst frequency information is not available, this can be obtained by the rate of change of the burst angle. Okay. So if the burst frequency information is not available, it is difficult to measure always but nowadays it is possible. We have many advanced technology, advanced devices, they can measure instant frequencies. which can be computed, right? For a very wide variation in the voltage, the aggregate static load is converted into constant impedance load for computational simplicity. Therefore, most of the time for stability analysis, we consider, unless there is a presence of very large motor, we always consider aggregate static load as constant impedance load for computational simplicity. In fact, constant impedance load representation has several computational benefits. Though IP part from the JIP part, IP part of the JIP load represents the static model of the motor loads. This representation is not accurate and can lead to erroneous conclusion. So IP part even doesn't represent properly this static model of load, motor loads if the motor is very large. So therefore, if the large motors are there, it is there in the system, that the actual model of the motor should be considered. Hence, for large motor loads, it is better to take the dynamics of the motors into consideration for stability studies. Okay, so let us see the motor models. Generally, we have practice of using the synchronous motors, large synchronous motors, and of course, large induction motors for industrial application. So now we can see the model of synchronous motor. Synchronous motor operational principle is almost same as the synchronous generator. So therefore, the modeling of the synchronous motor is not so actually different from the synchronous generator modeling. Only few changes, like the starter current in case of synchronous generator, we have taken, it is coming out of the winding of the starter. But here in case of synchronous motor, we'll take, it is going into the starter winding, right? Similarly, the torque developed in case of synchronous generator, it was subtracted from the mechanical torque in case of synchronous generator. But now, in case of motor, now the torque, the mechanical torque will be subtracted from the electromagnetic torque developed in the machine, right, in the motor. So therefore, dynamic equations representing the synchronous generator can be used for representing the synchronous motor with a modification, simple modification in swing equation. This is the modification we can see here. This previously in case of generator, we usually take Tm minus T plus D into delta omega, right? So now it is changing to T minus Tm plus D into delta omega. So it has to be also noted that in case of a synchronous motor, current into the starter should be taken as positive, unlike the case of synchronous generator. Right? So these are the only few changes, and this modeling remains same for both synchronous generator and motor. Therefore, we'll not talk much about the synchronous motor modeling. Now we'll jump to model of induction motor. So in case of induction motor, we know the starter of the induction machine is similar to the synchronous machine with a three-phase winding distributed symmetrically with 120-degree separation. The rotor of an induction machine also has three-phase windings distributed symmetrically with a 120-degree separation with same number of poles as that of the starter. A set of three-phase windings distributed symmetrically with 120-degree separation produces a pair of poles in the air gap that rotates at the synchronous speed. The three-phase rotor windings terminals are brought out to be connected to external resistance in case of a wound rotor induction machine and short-circuited in case of a squirrel cage induction motor. Of course, as per the design point of view, this is the fact. So for modeling purpose, both can be considered same with some assumptions. Some points to be noted here that the DQO transformation used for modeling synchronous machine can also be used for modeling induction machine as well. The rotor is the cylindrical here and hence has a uniform air gap, due to which there will be no difference between D-axis or Q-axis inductances and time constants. So previously we have seen in case of synchronous generator, The d-axis and q-axis inductances and time constants, they are different. We derived because of the saliency. But in case of cylindrical rotor, it will be same, right? So in case of synchronous machine, the d-axis was aligned with the rotor of the machine as it rotates at synchronous speed. So in case of synchronous generator, the rotor is rotating at synchronous speed in the steady state, right? And therefore the d-axis was considered aligned with the rotor axis. Okay. In case of induction machine, the rotor always rotates below the synchronous speed. It cannot achieve the synchronous speed. So its speed depends on the load torque required, right? So even the rotor of the induction machine rotates at slip speed. The rotor winding produces a synchronously rotating field, right? The rotor winding produces, this is important, synchronously rotating field with the same number of poles as that of the starter winding, right? Hence, a synchronously rotating DQ axis can be taken, which is neither fixed to the rotor nor fixed to the starter, and the three-phase rotor and starter quantities can be referred to this DQ axis, which is rotating at the synchronous speed. This DQ axis is synchronously rotating, actually in sync with the magnetic field, which is rotating on the rotor and starter, right? So the current in the rotor of an induction machine does not depend upon the excitation system, like in case of synchronous machine, but instead it depends on the relative speed between the synchronously rotating starter field and the rotor speed, that is the slip speed. So the same model can be used for induction motor and generator, and the main difference lies in the slip. Whatever model we'll see here, the same model is applicable, only the difference is slip, right? Now this is the equivalent circuit of the induction motor, we can say, consider induction motor. So now this is your rotor, okay, and this is your starter. Okay, now the starter also produces one magnetic field which rotates at the synchronous speed. Let us say it is rotating at omega s, and the rotor also produces a magnetic field which is rotating at omega s, same speed, right? And the rotor, let us say the rotor is rotating at omega r. Okay. So now if this is the axis, then what we'll see, let us say that rotor is making an angle of theta, and let us say theta is the angle made by the rotor with the reference axis. This is the reference. So then I can write theta equal to omega rt. Similarly, I know very well that S equal to slip equal to omega S minus omega R by omega S, and theta equal to omega RT, that is equal to 1 minus S into omega ST, right? And it is known to us. Now theta R is equal to, I can write it as here theta R. Theta R is omega ST minus theta, right? Okay. So omega RT, sorry, theta R is the angle made by this rotor, right? Or we can say the rotor and the synchronously rotating d-axis, right? So then theta R will be omega st, which is rotating here. Omega st is here. This one is omega st, right? Sorry, this is omega st. So omega st minus theta will be theta R. So that is nothing but is equal to S omega st, right? Now, if I'll take the derivative, d theta R by dt will be S omega S, right? Now, I can write the voltage equation concerning the rotor, and similarly, I can write the voltage equation of the starter, both, right? And again, I can write the equation for the flux linkage, right? So both in the starter and both in the rotor. So then I can take this transformation matrix, dq transformation matrix for starter as this, and for rotor it will be omega s minus omega rt, because the rotor is rotating in the synchronous, not in the synchronous speed, it is rotating below the synchronous speed. So therefore the relative speed into time is considered here in the transformation matrix. This is the only change. I think both the transformation matrix will be used to convert the equations of the stator and rotor respectively by multiplying this transfer matrix for stator and rotor both, right? Then after converting to dq axis or dq frame of reference, this is your flux linkage equation of the stator, this is the flux linkage equation of the rotor. And similarly, your voltage equation for the stator and rotor is mentioned here. Now I can derive the expression for the power of the rotor. So T equal to 3 by 2 P by 2 lambda Q or I dr minus lambda dr I QR. And now finally, again I have to convert it to power unit system. So after converting to power unit system, I will find different parameters: voltage, current, flux linkage, and the inductance values, right? Reactance values, right? Then I can write again, finally substituting this, converting into power unit system, I can write the voltage equation of the stator and then the flux linkage equation of the stator, right? Stator and rotor both. Okay, here both are there. This is the stator voltage equation, rotor voltage equation, stator flux linkage equation, and rotor flux linkage equation. And this is your torque equation, right? And finally, we'll get, this is your swing equation, right? So this is your swing equation. And then these are the equations concerned with the time constants, okay? Various time constants and the transient reactances, right? So this can be derived as we derived earlier for the synchronous generator, right? This is how we can model an induction motor, and similarly the induction generator also in the same equations, little change because of the slip for induction generator also can be modeled. So then we have seen here in the load model constant impedance model, then constant current, constant power model, then we have discussed the JIT model and the effect, to consider the effect of frequency. The frequency term is also added. And in order to incorporate the large motoring loads, we have developed the model for a synchronous motor and induction motor as well. Synchronous motor model is same as the synchronous generator except very little change, and induction motor model also we have seen. So today we have completed up to the modeling part, and then we'll stop here, okay? And next class, the representation of synchronous machine will be taught. Okay, thank you very much.